Hi you guys, so this week we're going to be focusing on the Grignard reaction, which is a classic and important reaction for organic chemists. It's important because it forms new carbon-carbon sigma bonds, and it's a named reaction, so it was named after Victor Grignard, who published the reaction in the year 1900 and received the Nobel Prize in Chemistry for that reaction in 1912. Okay, so we are first going to be doing a little review on the Grignard reaction. It was initially introduced in chapter, depending on the edition of the book you're using, either chapter 12 or chapter 13, but the alcohols chapter, because it's primarily used for the synthesis of alcohols. So to form a Grignard reagent, we first need to start with an alkyl or aryl halide. So for example, we have an aryl bromide, bromobenzene, excuse me, and propyl chloride. So different halogens can be used. Iodine is best, followed by bromine, followed by chlorine, and then different alkyl groups can be used. Can be primary, secondary, tertiary alkyl, can be aryl or vinyl. The only really consideration is not to have any acidic protons. But otherwise, it's a very generic reaction with lots of different R groups being able to be used. First, we treat it with magnesium metal, and magnesium metal then inserts between the carbon-halogen bond, forming what's called the Grignard reagent. If you look at the electronegativity difference between carbon and magnesium, the difference is about 1.2, which is pretty high. That means that the carbon-magnesium bond is definitely polar covalent, and it has quite a bit of ionic character. So sometimes the Grignard reagent is drawn with a line or a bond between carbon and magnesium, which is like drawing it as a polar covalent bond. Or sometimes it's drawn as an ionic compound with a positive and negative charge. But either way, it's just important to recognize that it is partially ionic and partially polar covalent. Because the carbon has a strong negative character, that carbon is both a strong nucleophile and a strong base. When it acts as a nucleophile, it can attack various electrophilic functional groups. Many of those contain the carbonyl group. And because the carbonyl carbon is electrophilic, a nucleophilic attack from the Grignard can take place on that carbon. And this arrow signifies resonance, or movement of the pi electrons up to the oxygen atom. The intermediate is typically called the tetrahedral intermediate, just because the carbon has changed from trigonal planar to tetrahedral. At the very end of the reaction, there will be what's called a quench. That's when water is introduced, or aqueous acid. And one of the functions of that is to protonate the negatively charged oxygen to make the OH group, which is a neutral and isolatable functional group. We can use Grignard reagents to make carbon-carbon bonds by attacking other functional groups as well. We've seen epoxides and esters before, and later in the semester, we'll see Grignard reactions with nitriles and acid chlorides, as well as carbon dioxide. The important thing to remember is that the Grignard reaction forms a new carbon-carbon sigma bond. Because the Grignard reagent is both a strong base and a strong nucleophile, care has to be taken to protect it from exposure to anything acidic. And that includes water, other alcohols, or anything else that contains an acidic proton. For example, if a Grignard reagent, which is represented by the R- here, is exposed to water, it can just pick up a proton from water to become an alkane. So for example, if you had used phenyl magnesium bromide, you would just get benzene. If you had used propyl magnesium chloride, you would get propane. So it would produce an alkane, and your Grignard reagent would not be present anymore and would not be able to perform a Grignard reaction. That is why we have to be careful to prevent it from being exposed to any water or anything else acidic. So when we use a solvent in the reaction, we typically want that solvent to be anhydrous. That just means that care is taken such that water is not present in the solvent. And ethers are commonly used as the solvent for organic reactions because the oxygen's lone pair coordinates to the positively charged magnesium, stabilizing it. These are some examples of some ether-based solvents that are commonly used in reactions as well as the Grignard reaction. We have diethyl ether, which is sometimes just called ether, tetrahydrofuran, and 1,4-dioxane. So ethers make great solvents, not just because they lone pairs have a slight negative charge and can help stabilize the magnesium with a positive charge, but also because they have low boiling points, so they're relatively easily removed from the reaction after it's conducted. And they're also polar aprotic, which means that they don't contain any acidic protons that might react with the Grignard reagent. Here are some examples of Grignard reagents reacting with various functional groups like ketone, aldehyde, or an ester. All of these are just the methyl magnesium bromide example of a Grignard reagent, but you can see the methyl in red. It could be any R group. It doesn't have to be just methyl. These are just the examples. When you react a ketone with a Grignard reagent, you end up with a tertiary alcohol. When you react an aldehyde with a Grignard reagent, you end up with a secondary alcohol. And when you react a ester with a Grignard reagent, you also end up with a tertiary alcohol. The difference is 2 of the Grignard reagent R groups have been incorporated into that tertiary alcohol. In this particular experiment this week, the video makers are making phenyl magnesium bromide, starting with bromobenzene, treating that with magnesium metal and ether, followed by the dropwise addition of benzaldehyde as the electrophile. Because we're treating a aldehyde with a Grignard reagent, our product is a secondary alcohol. You might call this diphenylmethanol, or sometimes it's called benzhydrol. Notice that the H3O plus is over the second step, so we only get the protonated alcohol after the acidic quench at the end of the reaction. Something that's important to note about Grignard reactions is that they're exothermic, and they often reflux once they get going without any supplied heat. How can that happen? That happens because they're often done in low boiling point solvents like diethyl ether. Diethyl ether's boiling point is something like 35, 37 degrees Celsius, something like that. It's very low. So oftentimes the heat that's given off in the reaction is enough to boil the solvent without any additional heat. Why do you then see people using some heat supplied at the beginning of the reaction? That's just to give the reactants enough energy to overcome the activation energy barrier to form the Grignard reagent. Once that's formed, it's all downhill in energy from there. So at the outset of the reaction, sometimes people will heat the reaction just a little bit by putting the flask in the palm of their hand, or they might supply it with a little bit of heated water at the very beginning, just to make sure the Grignard reagent forms well. Once it forms, it's exothermic, as we talked about, and gives off its own heat. And oftentimes after that, heat is not necessary unless you want to reflux for an extended period of time. Let's talk about the procedure. So for the procedure, the first thing you want to do is get your setup prepared, and the glassware needs to be completely free of water. That's what this video is there for. It shows the complete flame drying process of the entire glassware setup for the Grignard reaction, and I recommend that you take a look at this after watching this video. You can, I've uploaded the PowerPoint slides, so you can watch this video, and here's the link if you need it. So once you have the entire setup dry and free of any water present, then you will add some oven-dried magnesium turnings, which it's sometimes people grind up with a glass stirring rod or some other way of grinding up the magnesium just to expose a fresh surface of magnesium metal, because on the outside of the magnesium turnings is magnesium oxide. Magnesium oxide, it has formed from the reaction of magnesium with oxygen in the air, and that's essentially on the outside of all of the turnings. We don't want magnesium oxide for the reaction, we want the magnesium metal. So breaking up some of these chunks is helpful. In addition, the second thing you can do to expose the magnesium metal for the reaction is to add a few crystals of iodine. Iodine reacts with magnesium metal to form magnesium iodide. So once you've broken up a few of those turnings with your stir bar or with a spatula or your glass stirring rod, and you've exposed a little bit of magnesium, that iodine will find the magnesium that's exposed and it will start to react with it. And as it reacts with it, it's going to expose deeper pockets of magnesium metal. And the more surface of magnesium present, the faster the formation of the Grignard reagent will be. So it's basically there to remove the magnesium oxide coating and expose larger pockets of fresh magnesium metal to catalyze the Grignard reagent formation. Okay, so once we have the magnesium turnings and possibly some iodine in the solution or in the flask as well, there may or may not be a stir bar in there. You don't see one in here, but you could add one. At that point, you would add in some of your alkyl or aryl halide solution. So in this experiment, it would be adding in a solution of bromobenzene. So that's what that liquid is. It's a solution of bromobenzene in diethyl ether. Once the reaction starts to take place, sometimes it needs a little external heating, as we talked about in the palm of your hand or with some other heat source. The reaction will start to commence. And when that happens, the solution turns opaque or non-see-through. And you can start to see bubbles forming on the surface of the magnesium as it reacts with the bromobenzene, and magnesium salts forming, which is creating a non-see-through solution. As that continues, the magnesium continues to react and it starts to break down. It usually gets a darker color. Sometimes the solution takes on a color. It can be yellow or all the way to brown. And sometimes the color of the solution depends on just how fast you add the remaining bromobenzene solution. So we added a little bit at the outset. Once we started to see the reaction take place, that opaqueness forming, maybe some bubbles forming on the solution of the magnesium, then we start to add the rest of the bromobenzene solution dropwise. So that's why the volume here has gone up, and we can see bubbles. The bubbles are from the diethyl ether that is boiling because the reaction is exothermic. As I mentioned, there's some brown color that forms, and it tends to be even browner if you add the bromobenzene solution even faster into the solution. At this point, the reaction is often refluxed for at least 15 minutes or longer. During this time, a lot of the magnesium will have reacted, so the amount of magnesium present should go down substantially. And now we have a solution of the Grignard reagent that is ready to receive the electrophile. So the next thing we would do is prepare a solution of the electrophile. In this experiment, it is benzaldehyde. But as we mentioned, there's a lot of different electrophiles that could be used. It doesn't have to be an aldehyde. It could be a ketone, an ester, it could be carbon dioxide, a nitrile, an acid chloride, or a lot of other different electrophiles. So you prepare a solution of that electrophile and add that dropwise. It's important that the solvent that you use to prepare the solution is still dry. So it cannot have any water or other acidic protons. Again, that will react with the Grignard reagent and quench it such that it is not available to attack the electrophile. So sometimes, depending on the electrophile that's added, the reaction can be very colorful. For example, when phenylmagnesium bromide is prepared as the Grignard reagent, if you add in benzophenone en route to triphenylmethanol, we get a nice pink color for the solution after the benzophenone solution, which is a ketone solution, has been added. After that has stirred for a little while at room temperature, the reaction is ready to be quenched. Remember, to quench the reaction, that's when we introduce water and aqueous acid. Here's another video that you can watch that shows the addition of saturated aqueous ammonium chloride, which is an acidic aqueous solution, to quench a Grignard reaction. You could also additionally add aqueous HCl or aqueous H2SO4. All of those will do the job to quench the reaction. What does that involve? That involves adding, again, the water or the aqueous acid to the solution. A couple of things are going to happen during the quench. The first important function of adding the aqueous acid is to protonate the alkoxide ion. Notice you see after the Grignard reagent has reacted with an aldehyde, we get a magnesium alkoxide. It is only after you quench the reaction with H3O+ that you're able to have a neutral alcohol that you can isolate. So that is the first important function of the quench, or adding the aqueous acid at the end of the reaction. The second important function, and it's the reason why oftentimes aqueous acid is added instead of just water, which is to react with the excess magnesium metal in the reaction. You can see all of the magnesium turnings that remain at the end of the reaction, and we need to get rid of those because we don't want to isolate them or care about the magnesium after the reaction has taken place. So one of the great things about acid is that it reacts with magnesium metal, forms hydrogen gas, which bubbles out of solution, and it will take care of reacting any of the excess magnesium, convert it to a magnesium halide salt, like magnesium chloride or maybe magnesium sulfate, depending on the acid that's used. And then that will dissolve in the aqueous layer, and we'll be able to separate that during the extraction process. So once you have your two layers that will appear after quenching the reaction, again, the two layers are an aqueous acid layer that you added and the diethyl ether, which will form the organic layer. Those are the two layers that are present after the quench. You can directly pour that mixture into a separatory funnel. The top layer should be the ether layer or the organic layer, and it should contain the product because the product is a neutral alcohol, so it should be much more soluble in diethyl ether than it is in water. The bottom layer will be the aqueous acid, and we'll be able to drain that out. That will contain a lot of the magnesium salt byproducts in the reaction, which we want to remove from our mixture. Once we've drained out the aqueous acid, it's common to sometimes use an aqueous sodium bicarbonate wash. That will just remove any trace acid from the organic layer. Next, we would add in an aqueous brine solution. The brine solution is a saturated salt solution. So because the water is saturated with salt, it actually attracts more water. So it will dry out the organic layer by removing some of the water from the organic layer, creating a more dilute brine solution in the process. Once we have drained all three of those aqueous layers, so again, the first aqueous was the aqueous acid that we added during the quench. Next, optionally, some people will add aqueous sodium bicarbonate. We can drain that. Again, that will remove any trace acid from the organic layer. Then the aqueous brine. Again, all of those layers, those aqueous layers will be the bottom layer, so it's very easily drained from the separatory funnel without having to remove the ether organic layer from the separatory funnel at any time. So lastly, we'll be left with just the organic layer in the separatory funnel. We can drain that into an Erlenmeyer flask and further dry the organic layer with sodium sulfate or magnesium sulfate. That will again remove the last trace amounts of water that could be present in the organic layer, and it will be ready for transfer to a round bottom flask and removal of the diethyl ether solvent via a rotary evaporator. Once you have the crude product, it often needs a recrystallization or other type of purification process to completely purify it. The product is commonly mixed with some biphenyl. Biphenyl is formed from the reaction of the Grignard reagent with bromobenzene in an organometallic reaction. This type of reaction will be covered at the very end of the semester in your lecture course. But the only thing I'll say about it now is just that it is not an SN2 reaction to make biphenyl. Because of course we don't do SN2 reactions on sp2 hybridized carbons. So because there's some of this as a byproduct, and potentially other byproducts could be excess of the electrophile, so excess benzaldehyde, excess bromobenzene that may be unreacted in the reaction. So all of those can potentially be contaminants of the product. We can do a process of purification, for example, a recrystallization. And that's what the second video in the activity is for. It takes you through the recrystallization using petroleum ether as a solvent. Interestingly, petroleum ether is actually a mixture of hydrocarbons and it's not an ether at all. But once it's dissolved, you can cool it down. Hopefully you'll get crystals forming and you will be able to isolate the crystals, which will hopefully be some pure product. If not, maybe a second recrystallization process would have to take place. Okay, that's the end of the pre-lab video. As always, I'll see you in office hours and let me know if you have any questions.